I'm going to study the chapter Chemical Equilibrium from Pardeep's book by Dr. S.C. Khetrapal. Chapter 4 Chemical Equilibrium 4.1 Recapitulation of the earlier studies. First, reversible reactions. A reaction in which not only the reactants react to form the products under certain conditions, but the product also react to form the reactants under the same conditions is called reversible reaction. In other words, a reaction which takes place not only in the forward direction but also in the backward direction under the same conditions is called reversible reaction. These are represented by putting a double arrow between the reactants and the products. A few examples of the reversible reactions are given below. First, homogeneous reactions. These are those reactions in which all the reactants and the products are present in the same phase. A. In the gaseous phase, H2 plus I2 is in equilibrium with 2HI gas. N2 plus 3H2 is in equilibrium with 2NH3. B. In the liquid phase, acetic acid plus ethyl alcohol is in equilibrium with ethyl acetate plus water. Second, heterogeneous reactions. These are the reactions in which the reactant and the products are present in two or more than two phases. Iron solid plus water gas is in equilibrium with Fe3O4 solid plus hydrogen gas. Calcium carbonate, that is solid, is in equilibrium with calcium oxide, that is solid, plus carbon dioxide, that is gas. Second, irreversible reactions. If a reaction cannot take place in the reverse direction, that is, the products do not react to give back the reactants under the same conditions, is called an irreversible reaction. It is represented by putting a single arrow between the reactants and the products, pointing from the reactant towards product. A few examples of irreversible reactions are given below. 2KClO3 solid is equal to 2KCl plus 3O2. AgNO3 aqueous plus NaCl aqueous is equal to AgCl solid plus NaNO3 aqueous. BaCl2 aqueous plus Na2SO4 aqueous is equal to BaSO4 gas plus 2NaCl solid. 2Mg solid plus O2 gas is equal to 2MgO solid. Third, chemical equilibrium. In a reversible reaction, in the beginning, the rate of flow of reaction is maximum and the rate of backward reaction is minimum because the concentrations of reactant are maximum and those of the products are minimum. As the time passes, the reactants are consumed and the products are formed more and more. That is, the amount of reactants are decreasing while those of the products are increasing. Hence, the rate of forward reaction is decreasing while the rate of backward reaction is increases with passage of time. Ultimately, a stage comes when the rate of forward reaction becomes equal to rate of backward reaction. The reaction is then said to have attained chemical equilibrium. Hence, chemical equilibrium may be defined as follows. In a reversible reaction, when the rate of forward reaction becomes equal to the rate of backward reaction, the reaction is said to be in chemical equilibrium. It is important to mention that at equilibrium, since the rate of forward reaction is equal to the rate of backward reaction, this means that at equilibrium, as much of the reactant reacts to form products in a particular time, the same amount of product reacts to give back the reactant in the same time. Hence, at equilibrium, the concentration of each of the reactants and the products remain constant, provided the temperature remains constant. Further, it may be noted that at equilibrium, the reaction does not stop. The forward as well as backward reaction are going, but at equal speeds. Hence, the equilibrium is dynamic in nature and not static. 4. Law of mass action. It states that the rate at which a substance reacts is proportional to its active mass and hence the rate of chemical reaction is proportional to the product of the active masses of the reactants. The term active mass means molar concentration, that is the number of moles per liter. It is represented by putting the formula of the substance in square brackets. For example, active mass of a substance A is represented by A. 5. Chemical law of equilibrium. Law of chemical equilibrium. The result obtained by applying the law of mass action to a reversible reaction in equilibrium is called the law of chemical equilibrium. For example, consider the general reversible reaction. A plus B is equal to M plus NN. According to law of mass action, rate of forward reaction is directly proportional to A raised to power concentration of A raised to power coefficient of A, B concentration of B raised to power coefficient of B. It is equal to Kf concentration of A into concentration of B, where Kf is a constant of proportionality and is called the rate constant for the forward reaction. Rate of forward reaction reaction is directly proportional to concentration of M raised to power coefficient of M, concentration of N raised to power coefficient of N, that is equal to Kb into concentration of M raised to power coefficient of M into concentration of N raised to power coefficient of N, where Kb is a constant of proportionality and is called rate constant for the backward reaction. At chemical equilibrium, rate of reaction is forward reaction is equal to rate of backward reaction. Kf concentration of A into concentration of B is in equilibrium with Kb is concentration of M into concentration of N. That is Kf by Kb is equal to concentration of M into concentration of N divided by concentration of A into concentration of B. As Kf and Kb are constant temperature at constant temperature, hence the ratio Kf by Kb is also constant at constant temperature. It is usually represented by K and is called equilibrium constant. Thus, the above equation may be written as concentration of M raised to power coefficient of M into concentration of N raised to power coefficient of N divided by concentration of A raised to power coefficient of A, concentration of B raised to power coefficient of B is equal to K. This expression is called the law of chemical equilibrium and may be expressed in words as follows. The products of the molar concentrations of the product each raised to the power equal to its coefficient divided by the product of molar concentrations of reactants each raised to its coefficient is constant at constant temperature and is called equilibrium constant. 4.2 Types of equilibrium constants and relationship between them. If molar concentrations are used in the expression for the law of chemical equilibrium, the equilibrium constant is called the equilibrium constant in terms of concentrations and is represented by Kc. On the other hand, if the various reactants and products, that is A, B, M, N, etc. are gaseous, instead of molar concentrations, partial pressures are used. The equilibrium constant is then called the equilibrium constant in terms of pressures and is represented by Kp. However, the most appropriate quantity to be used in place of molar concentration of or pressure is the activity of each reactant in product. Then, the equilibrium constant in terms of activities is represented by Ke. Thus, the general reversible reaction we may have concentration of M raised to power M into concentration of N raised to power N divided by concentration of A raised to power small a into concentration of B raised to power small b is equal to Kc, or Pm raised to power small m Pn raised to power small n divided by Pa raised to power small a into Pb raised to power small b is equal to Kp. There is also equilibrium constant in terms of mole fractions, which is usually represented by Kx. Its value is given by Kx is equal to molar mass of M raised to power small m, molar mass of N raised to power small n divided by molar mass of A raised to power small a, molar mass of B raised to power small b, whereas Xa, Xb, Xm, Xn, etc. represent mole fractions of A, B, M, N, etc. respectively at equilibrium. A. Relationship between Kp and Kc. Consider the general reversible reaction. Small a plus B, capital B, is in equilibrium with M, capital M plus N, capital N. If the equilibrium constant of this reaction is expressed in terms of concentrations, we may write Kc is equal to concentration of M raised to power small m into concentration of n raised to power small n divided by concentration of A raised to power small a plus into concentration of B into raised to power small b. Or simply as Kc is equal to concentration of m raised to power small m concentration of n raised to power small n divided by concentration of A raised to power small a plus into concentration of B raised to power small b, where Ca, Cb, Cm and Cn represent the molar concentrations of A, B, M and N respectively. If A, B, M and N are gaseous, the equilibrium constant for the above reaction may be expressed in of pressure as Kp is equal to partial pressure of m raised to power m into partial pressure of n raised to power small n divided by partial pressure of A raised to power small a into partial pressure of B raised to power small b. If the gases are supposed to be ideal, we can apply the ideal gas equation PV is equal to nRT, or P is equal to n by V RT is equal to CRT, where C is equal to n by V is the number of moles per liter, that is, it's the molar concentration. For the gaseous substances A, B, M and N, we may write Pa is equal to CART, Pb is equal to CBRT, Pm is equal to CMRT, Pn is equal to CNRT. Putting these values in equation 4, we get Kp is equal to CMRT raised to power small m, CNRT raised to power small n divided by CART raised to power small a into CBRT raised to power small b, from where we get Kp is equal to Kc dot RT raised to power del n. Del n is equal to m plus n minus a plus b, that is number of moles of product minus number of moles of reactants is equal to change in the number of moles. So Kp is equal to Kc RT raised to power del n. B. Relationship between Ka and Kp or Kc. As activity is related to the composition variable x, concentration of or pressure by the equation alpha is equal to gamma into x, or activity is equal to gamma into x, where gamma is the activity coefficient of a substance at the given composition. The expression for Ka as given in equation 1 can be written as Ka is equal to K gamma into Kx. If pressures are used, then activity of any component is related to its partial pressure in the mixture by the equation Ai is equal to gamma I Pi, then Ka is equal to K gamma Kp. If concentrations are used, we may write for each component A is equal to gamma C, where C is molar concentration, then K is equal to K gamma Kc. It may be noted that Ka is the only true constant for a reaction at a given temperature and is called thermodynamic equilibrium constant. K gamma is not constant, but its value depends upon the nature of the gas involved and the temperature and the total pressure, or on the concentration of reactants and the products, and hence Kp and Kc are also not constant even at constant temperature. However, for ideal gases or for real gases at very low pressure, gamma is equal to 1 for each gas, then K gamma is equal to 1 and hence Ka is equal to Kp. Similarly, in the case of very dilute solutions, as concentration is almost 0, gamma is almost 1, Ka is equal to Kc. C. Relationship of Kx with Kp and Kc. The partial pressure P of any gas in a mixture of ideal gases is related to the total pressure P according to the expression small p is equal to x capital P. Substituting these values in equation 4, we get Kp is equal to Kx P raised to power del n. Combining this equation with equation 5, we get Kc is equal to Rt raised to power del n is equal to Kx P del raised to power del n, or Kc is equal to Kx into P by Rt whole raised to power del n is equal to Kx V del n, where V is the volume of the system containing 1 mole of the gas, that is, it is equal to the total volume divided by total number of moles. It is interesting to note that if del n is equal to 0, all the equilibrium constants are identical, but otherwise they differ. Further, it is important to note from equation 10 and 11 that the relation between Kx and Kp or Kc involves total pressure or volume of the system. Hence, where Kp and Kc vary only with temperature, Kx varies with pressure also unless delta n is equal to 0. For this reason, Kx is usually not used for gaseous reactions. 4.3 Units of Kp, Kc, and Ka. Since partial pressures are expressed in atmospheres, therefore, from equation 4 it follows that the dimensions of Kp will be atmosphere raised to power del n. Similarly, since the concentrations are expressed in mole per liter, according to equation 3, Kc will have the dimensions mole per liter whole raised to power del n. It is only when del n is equal to 0 that Kp and Kc will be pure numbers. However, in the conventional writings, the units are omitted in specifying the values of Kp and Kc, but for precise work, it is better to include them. In case of activities, as these are dimensionless quantities, Ka has no unit. According to the latest conventions, even Kc and Kp are taken as dimensionless because all concentrations are taken with respect to reference standard state concentration of 1 mole per liter, and all pressures are taken with respect to standard state pressures of 1 atmosphere. 4.4 Concept of chemical potential. 4.4.1 Partial molar quantities. During the discussion of the various thermodynamic properties so far, it was supposed that the system is a closed system, so that the mass or the composition of the system remains constant, and the variation in the thermodynamic properties was studied only with respect to the temperature and pressure. G. N. Lewis in 1907 introduced the concept of the variation in a thermodynamics property for an open system, in which the composition of one or more of the component is varied. That is, when some quantity of a component is added to the system or removed from the system. Obviously, such a variation will be observed only in an extensive property, that is, a property which depends upon the quantity of the mass contained in the system. Consider any extensive property such as volume, free energy, entropy, energy content, etc. Let it be represented by general by X. Suppose that the system contains of n constituents in a solution or in a heterogeneous system, the amount of which present in the system are n1, n2, n3 moles. Then the property X is a function not only of temperature and pressure but of the amounts of the different constituents as well. So that we can write X is a function of temperature, pressure, n1, n2, n3 and so on. Now, if there is a small change in the temperature, pressure and the amounts of constituents, the change in property X will be given by dx is equal to del x by del t, where pressure n1 and n2 are constant, dt plus del x by del p, where temperature n1 and n2 are constant, dp plus del x by del n1, where T temperature, pressure and n2 n3 are constant, dn1 plus del x by del n2, temperature, pressure n1 and n3 are constant, dn2 plus so on. On the right hand side, the first quantity gives the change in the value of X with temperature when pressure and composition are kept constant. The second quantity gives the change in the value of X with pressure when temperature and composition are kept constant. The remaining quantities give the change in the value of X with the change in the amount of the constituent when temperature, pressure and the amount of other constituents are kept constant. If the temperature and pressure of the system are kept constant, then dt is equal to 0 and dp is equal to 0. So the equation 2 becomes dx at constant temperature and pressure is equal to del x by del n1 at constant temperature, pressure, n2 and n3, dn1 plus del x by del n2 at constant temperature, pressure, n1, n3, dn2 plus so on. Each derivative on the right hand side is called the partial molar quantity and is represented by putting a bar over the symbol of the particular property, that is x1 bar, x2 bar for the first, second component, etc. respectively. Thus, del x by del n1 at constant temperature, pressure, n2, n3 is equal to x1 bar. Del x del n2 at constant temperature, pressure, n1, n3 is equal to x2 bar, etc. In general, for any component I, del x by del n1 at constant temperature, pressure, n1, n2 is equal to xi bar. Thus, for the ith component of in a system, partial molar internal energy is equal to del U by del nith at constant temperature, pressure, n1, n2 is equal to ui bar. Partial molar enthalpy, del H by del nith at constant temperature, pressure, n1, n2 is equal to hi bar. Partial molar entropy is equal to del S by del ni at constant temperature, pressure N1, N2 is equal to SI bar. Partial molar volume del V by del N ith at constant temperature, pressure N1, N2 is equal to VI bar. 4.4.2 Chemical potential, partial molar free energy. If the extensive property under consideration is the free energy G, can be written as del G by del Ni at constant temperature, pressure N1, N2 is equal to Gi bar. This quantity is called partial molar free energy or chemical potential and is usually represented by the symbol mu. Thus, mu is equal to Gith bar is equal to del G by del Ni at constant temperature, pressure N1, N2. If d Nith is equal to 1 mole, mu is equal to dG at constant temperature, pressure N1, N2. Hence, the chemical potential may be defined as the chemical potential of a constituent in a mixture is the increase in the free energy which takes place at constant temperature and pressure when 1 mole of that constituent is added to the system, keeping the amounts of all other constituents constant. That is, when 1 mole of constituent is added to such a large quantity of the system that its composition remains almost unchanged. For free energy as the extensive property, equation 3 can be written as del G at constant temperature and pressure is equal to del G by del N1 at constant temperature, pressure N2, N3 dN1 plus del G by del N2 at constant temperature, pressure N2, N3 dN2 plus so on, or dG at Tp is equal to mu1 dN1 plus mu2 dN2 plus so on. For a system of definite composition represented by the number of moles N1, N2, N3 etc. of different constituents, equation 7 on integration gives GTPN is equal to N1 mu1 plus N2 mu2 plus so on, where the subscript N stands for constant composition. On the right hand side, the first term gives contribution of the first constituent to the total free energy of the system. The second term gives to the contribution of the second constituent and so on. Obviously, mu1 and mu2 etc. give the contribution per mole to the total free energy. Hence, chemical potential may be defined as under the chemical potential of a constituent in a mixture is its contribution per mole to the total free energy of the system of constant composition at constant temperature and pressure. It may be noted that whereas free energy is an extensive property, the chemical potential or in general any partial molar property is an intensive property. Further, the concept of chemical potential is very useful in the deduction of number of laws of physical chemistry such as law of chemical equilibrium, distribution law, phase rule, etc. 4.5 Free energy change in a chemical reaction. Like internal energy or heat content, every substance is associated with a definite value of free energy, G, already defined by the equation G is equal to H minus Ts, depending upon the conditions of temperature and pressure. Further, just as the absolute value of internal energy or heat content associated with the substance cannot be determined, so is the case with free energy. Fortunately, the absolute values of these quantities are not required. We are usually interested to know only the changes in free energy accompanying the different reactions. The change in free energy del G accompanying a reaction is given by the equation del G is equal to free energy of the products minus free energy of the reactants. Del G is equal to G products minus G reactants. Let us consider the general reversible reaction. Remembering that in a mixture, the free energy per mole of any component is called its chemical potential denoted by nu. The free energy change for the above reaction will be written as where mu1, mu a, mu b, mu m, mu n etc. represent the chemical potentials of A, B, M, N etc. respectively in the chemical reaction mixture. 4.6 Standard state free energy change in a chemical reaction. If all the reactants and products of a chemical reaction are taken in the standard state, the free energy change accompanying the reaction is called standard state free energy change and is represented by delta G naught. The standard state of the substance is the state at which the temperature is 25 degrees Celsius and the concentration is unity. If the substance is present in the form of solution or the pressure is 1 atm or if the substance is gaseous. Thus, the standard state free energy change accompanying the reaction is given by del G naught is equal to G naught product minus G naught reactant. In terms of activities, the standard state of a substance in the state at which activity of a substance is unity. 4.7 Predicting spontaneity of a reaction in terms of free energy change. As described above, the free change accompanying a reaction is given by del G is equal to G product minus G reactant. A reaction can occur that is spontaneous if it is accompanied by the decrease in free energy, that is G product is less than G reactant. Under this condition, del G is negative. Hence, a reaction is spontaneous if delta G is negative. This aspect has already been explained in chapter 2 also. Similarly, if delta G is positive, the reaction will be non-spontaneous. The same criteria apply if we consider standard free energy change, delta G naught, in the place of free energy change, delta G. 4.8 Chemical equilibrium in terms of free energy change. It has already been mentioned above that every substance is associated with a definite value of free energy, depending upon the conditions of temperature, pressure. In the beginning, the amounts of the reactants are maximum, while those of products are minimum, almost equal to zero. Hence, the free energy associated with the reactants is maximum, while that associated with the products is minimum. As the reaction proceeds, the reactants are consumed while the products are formed. In other words, the amount of the reactants are decreasing while those of the product is increasing. As a result, the free energy of the reactants keeps on decreasing while that of the products keep on increasing. And consequently, the free energy change accompanying the reaction keeps on changing. Ultimately, when the reaction attains equilibrium, the concentration of each of the reactants and the products become constant, and the free energy of the reactants become equal to the free energy of the products. Now, so long as temperature and pressure are kept constant, there is no further change in free energy. In other words, at the point of equilibrium, delta G is equal to 0. These changes are represented diagrammatically in figure 4.2. Another interesting question that arises with regard to chemical equilibrium is, in a reversible reaction, the forward as well as backward reaction takes place. Since the conditions for the spontaneity of a reaction is that delta G should be negative, this means that delta G is negative for forward as well as for backward reaction. How? The reaction to the above question can be understood by considering the following reversible reactions. N2O4 gas is in equilibrium with 2NO2. The standard free energy change for this reaction is plus 5.40 kilojoule. Since delta G naught is positive, one might predict that N2O4 is in standard state at 298 Kelvin and 1 atm, would not dissociate into NO2 at all, that the reverse reaction, that is formation of N2O4 from NO2, would go to completion. However, both these predictions are incorrect. The reaction is reversible and we know that the reversible reactions tend to go in equilibrium and not to completion. Moreover, the forward as well as the backward reaction should be spontaneous. The free energy of the system in which the above reaction occur at 298 Kelvin and 1 atm is plotted against the fraction of N2O4 dissociated in figure 4.3. Point A represents the standard free energy of 1 mole of N2O4. Point B represents the standard free energy of 2 moles of NO2, and the other point between A and B on the curve represents the free energy of mixtures of N2O4 and NO2. The free energy curve exhibits a minimum at the equilibrium point E, whereas 16.6% of N2O4 is dissociated. The difference between the standard free energy of 2 moles of NO2 at point B and the standard free energy of 1 mole of N2O4, delta G naught for the reaction is plus 5.40 kilojoule. However, as shown in figure 4.3, the free energy of the reaction mixture at the equilibrium point E is less than either of the pure reactant A or product B. In the present example, the point E is lower by 0.84 kilojoule than the point A. This means that when 1 mole of N2O4 changes into the equilibrium mixture, the value of delta G naught is equal to minus 0.84 kilojoule. Similarly, when 2 moles of NO2 changes into the equilibrium mixture, hence the delta G naught is equal to minus 5.40 plus minus 0.84 is equal to minus 6.24 kilojoule. Thus, in both the cases, the value of delta G naught is negative, and hence both the processes, that is forward reaction as well as backward reaction, are spontaneous. 4.9 Calculation of standard free energy change in a reaction. The expression for the calculation of free energy change of a gaseous system when the temperature remains constant and the pressure changes has already been derived in chapter 2. The expression is delta G is equal to nRT natural log of P2 by P1. The standard free energy change of a reaction is usually calculated by any one of the following methods. 1. From experimentally determined values of the equilibrium constant Kp or Kc and using the expression delta G naught is equal to minus RT natural log of Kp, or delta G naught is equal to minus RT natural log of Kc. Second, from experimentally determined values of entropies and heat of reaction and using the expression delta G naught is equal to delta H naught minus T delta S naught. The heat of reaction delta H naught is found directly from experiments and the entropy change delta S naught is calculated from the values of absolute entropies of the various substances involved using the equation. Delta S naught is equal to summation of delta S naught of products minus summation of delta naught of reactants. Third, from standard free energy of formation. Like the standard heat of formation, standard free energy of formation is defined as the free energy change accompanying a reaction in which 1 mole of the substance in its standard state 25 degrees Celsius 1 atm pressure is formed from its elements in their standard states. It is represented by delta Fg naught. Assuming, as in the case of heat of formation, that the free energies of formation of the element in their standard states are zero, the free energy change of any reaction can be calculated using the expression delta G naught is equal to summation of delta Fg naught of products minus summation of delta Fg naught of reactants. 4.10 Criteria of equilibrium in terms of intensive properties: temperature, pressure, and mu. As already explained in chapter 1, a system is said to be in equilibrium if the following equilibria exist simultaneously. First, thermal equilibrium, second, mechanical equilibrium, third, chemical equilibrium. These equilibria imply respectively the constancy of temperature, pressure, and chemical potentials. These may be derived as follows. First, condition of temperature. As explained in chapter 2, for thermodynamic equilibrium, ds at constant internal energy and volume is equal to 0. This means if ds1 is the entropy change in one part of the system and ds2 is in the other part of the system, or for two phases in equilibrium, if ds1 is entropy change of phase 1 and ds2 that of phase 2, then ds1 plus ds2 is equal to 0. If del Q is the heat lost by part 1 or phase 1 which is gained by part 2 or phase 2, can write as ds1 is equal to del Q by T1 and ds2 is equal to minus del Q by T2. Substituting in equation 1, del Q divided by T1 minus del Q divided by T2 is equal to 0, or T1 is equal to T2. Second, conditions of pressure. As explained in chapter 2, for thermodynamic equilibrium, dA at constant temperature and volume is equal to 0. Proceeding as above, we can write dA1 plus dA2 is equal to 0. As the work involves is the pressure volume work, if dV is the small decrease in the volume of phase 1, there will be increase in volume equal to dV in phase 2 because overall volume remains constant. Hence, dA1 is equal to minus P1 dV and dA2 is equal to P2 dV. Substituting in equation 2, we get minus P1 dV plus P2 dV is equal to 0, or P1 is equal to P2. Third, condition of chemical potential. As explained in the chapter 2, the thermodynamic equilibrium dG at constant temperature and pressure is equal to 0. As before, we have dG1 plus dG2 is equal to 0. If mu1 plus mu2 are the chemical potentials of the substances in phase 1 and 2 respectively, and dn moles of are transferred from phase 1 to phase 2, we have mu1 minus dn plus mu1 into minus d1 plus mu2 dn is equal to 0, or mu1 is equal to mu2. 4.11 Thermodynamic derivation of the law of chemical equilibrium. Consider the general reversible reaction. If the chemical potentials of A, B, etc. are mu1, mu A, mu B, etc. respectively, and those of M and etc. are mu M, mu N, etc. respectively, then under conditions of constant temperature and pressure, total free energy of reactant is equal to A mu A plus B mu B plus so on. Total free energy of products is equal to m mu m plus n mu n plus so on. Free energy change accompanying the reaction at constant temperature and pressure will be delta G is equal to summation of G products minus summation of G reactants is equal to m mu m plus n mu n plus so on minus a mu a plus b mu b plus so on. However, when the system is in equilibrium at constant temperature and pressure, delta G is equal to 0. Hence, m mu m plus n mu n plus so on minus a mu a plus b mu b plus so on is equal to 0. M mu m plus n mu n plus so on is equal to a mu a plus b mu b plus so on. This is general thermodynamic condition for equilibrium in any reversible chemical reaction, which is applicable to all type of systems. If all the reactants and products are ideal gases, the chemical potential of any component in the ideal gas mixture is given by mu is equal to mu naught plus RT natural log of P, where P is the partial pressure of the given gas in a mixture of mu naught is the chemical potential in the standard state. That is, when partial pressure is 1 atm, whose value depends only on temperature. Substituting mu A is equal to mu A naught plus RT natural log of PA, mu B is equal to mu V naught plus RT natural log of PB, etc. in equation 5, we get natural log of Pm raised to power small m plus Pn raised to power small n divided by Pas raised to power small a into Pb raised to power small b is equal to minus delta G naught of reaction divided by RT, or Pm raised to power small m into Pn raised to power small n divided by Pa raised to power small a into Pb raised to power small b is equal to E raised to power minus delta G naught divided by RT. As standard free energy change, delta G naught depends only on temperature, hence a constant temperature. Right hand side of the above equation is constant at constant temperature. This implies that for an ideal gas system at constant temperature, Pm raised to power small m into Pn raised to power small n divided by Pa raised to power small a into Pb raised to power small b is equal to constant, that is Kp. If molar concentrations are taken instead of partial pressures, the chemical potential of any component will be given by mu is equal to mu naught plus RT natural log of C, where C is the molar concentration of the components in the reaction mixture and mu naught is the chemical potential of the substance in the standard state, that is when the concentration is 1 mole per liter. Proceeding exactly in the same manner as above, it can be shown that concentration of m raised to power small m, concentration of n raised to power small n divided by concentration of A raised to power small a into concentration of B raised to power small b is equal to Kc, where all concentrations are at equilibrium. For derivation of a chemical law of chemical equilibrium in terms of mole fractions, we use the relation mu is equal to mu naught x plus RT natural log of x, where x is the mole fraction and mu naught x depends on the temperature and pressure. Substituting these values of mu in equation 5 and proceeding exactly in the same way, we get mole fraction of m raised to power small m, mole fraction of n raised to power small n divided by mole fraction of A raised to power small a into mole fraction of B raised to power small b is equal to constant, that is Kx. 4.12 Relationship between standard free energy change and equilibrium constant. It has been derived in equation 7 above that delta G naught is equal to minus RT natural log of partial pressure of m raised to power small n partial pressure of small n raised to power small n partial pressure of A raised to power small a partial pressure of B raised to power small b. Putting all values, delta G naught is equal to minus RT natural log of Kp, thus knowing delta G naught of a reaction, the equilibrium constant Kb can be calculated or vice versa. Similarly, it can be shown that delta G naught is equal to minus RT natural log of Kc. Delta G naught is equal to minus RT natural log of Ka. As before, knowing delta G naught of the reaction, Ka or Kc can be calculated and vice versa. It is important to note that as Kp and Kc have different values, unless number of moles of products is equal to number of moles of reactants. Therefore, the values of delta G naught obtained by using Kp and Kc are different. 4.13 Van't Hoff reaction isotherm. Consider the general reversible reaction. If for any state other than the standard state, mu A, mu B, etc. are the chemical potential, partial molar free energies of A and B, etc., respectively, and mu m and mu n, etc., are the chemical potentials of m, n, etc., respectively. Then, under conditions of constant temperature, pressure, and composition, we have total free energy of the reactants is equal to A mu A plus B mu B plus so on. Total free energy of the products is equal to m mu m plus n mu n plus so on. Therefore, free energy change accompanying the reaction at constant temperature and pressure will be delta G is equal to summation of delta G products minus summation of delta G reactants. Assuming that A, B, M, N, etc. are gaseous, the chemical potential mu of any component for any state is given by mu is equal to mu naught plus RT natural log of P, where mu naught is the chemical potential in the standard state. That is when partial pressure of 1 atm and partial P is the partial pressure of that gaseous component in the mixture under the given state other than the equilibrium state. Substituting mu A is equal to mu naught A plus RT natural log of PA, mu B is equal to mu naught B plus RT natural log of B, etc. In equation 1 we get delta G is equal to m mu naught m plus RT natural log of Pm plus n mu naught n plus RT natural log of Pn plus so on minus E into mu naught A plus RT natural log of PA plus B mu naught B plus RT ln of PB plus so on. On rearrangement of these terms we get delta G is equal to delta G naught plus RT natural log of partial pressure of m raised to power small m, partial pressure of n raised to power small n divided by partial pressure of A raised to power small a, partial pressure of B raised to power small b. Further, in equation 2, the ratio partial pressure of m raised to power small m, partial pressure of n raised to power small n divided by partial pressure of A raised to power small a, partial pressure of B raised to power small b is similar to the values for equilibrium constant Kp. But it is not equal to Kp because Pa, Pb, Pm, Pn, etc. are not the partial pressures are at equilibrium, but for any other state the factor partial pressure of m raised to power small m into partial pressure of n raised to power small n divided by partial pressure of A raised to power small a into partial pressure of B raised to power small b is therefore simply called the pressure quotient or the reaction quotient, and is usually represented by Qp. Hence, equation 3 may be written as delta G is equal to delta G naught plus RT natural log of Qp. This equation gives the free energy change of the reaction in terms of standard free energy change and a factor depending upon the partial pressures of the components in the reaction mixture under the given state at constant temperature T. That's why equation 4 is called reaction isotherm. The equation was put forward by J.H. Van 't Hoff's 1886, hence it is called as Van 't Hoff's reaction isotherm. Alternative derivation of law of chemical equilibrium. Starting from equation 3, the law of chemical equilibrium can be derived thermodynamically as follows. For a reversible reaction in equilibrium, we know that delta G is equal to 0. If at equilibrium the partial pressures Pa, Pb, Pm, Pn, etc. becomes equal to P dash A, P dash B, P dash M, P dash N, etc. respectively, then substituting these values in equation 3 and putting delta G naught is equal to 0 for the equilibrium, we get delta G naught is equal to minus RT natural log of P dash M raised to power small m, P dash N raised to power small n divided by P dash A raised to power small a, P dash B raised to power small b. But delta G naught in the standard free energy change for the given reaction and is the constant quantity at constant temperature. Hence, the term on the right hand side of the above equation must also be constant. Thus, if the temperature is constant, we must have Kp. Kp is equilibrium constant because P dash A, P dash B, P dash M, P dash N, etc. are the partial pressures at equilibrium. 4.14 Calculation of free energy change of reaction in any state. From equation 3 of section 4.13 we have delta G is equal to delta G naught plus RT, natural log of partial pressure of m raised to power small m partial pressure of n raised to power small n divided by partial pressure of a raised to power small a partial pressure of b raised to power small b. From equation 5 of section 4.13, we have delta G naught is equal to minus RT natural log of p dash m raised to power small m p dash n raised to power small m divided by p dash a raised to power small a p dash b raised to power small b. Substituting the values of delta G naught from the equation in equation 1, we get delta G is equal to minus RT natural log of Kp plus RT natural log of Kq, where Kp and Kq are equilibrium constant and pressure quotient as already explained. Equation 3 or equation 4 can be used to calculate the free energy change of a reaction at any state. Equation 4 is another form of Wentz-Hoff reaction isotherm. 4.15 Variation of equilibrium constant with temperature, Wentz-Hoff's equation or reaction isochore. In the previous discussion, it has been mentioned over and over again that for any reaction, equilibrium constant is constant only at constant temperature. In other words, the value of equilibrium constant of any reaction changes with the change of temperature. The expression giving the exact variation of the equilibrium constant with temperature was originally put forward by Wentz-Hoff and hence is called Wentz-Hoff equation. It may be derived as follows. The equation constant Kp is related to the standard energy delta G naught according to the equation delta G naught is equal to minus RT natural log of Kp. Differentiating this equation with respect to the temperature at the constant pressure. Then multiplying this equation throughout by T. Putting minus RT natural log of Kp is equal to delta G naught. This equation becomes this. According to Gibbs-Helmholtz equation, we know that delta G is equal to delta H plus T into del delta G divided by del T at constant pressure. In a special case, when all the substances are in their standard states, Gibbs-Helmholtz equation can be written as delta G naught is equal to delta H naught plus T into del delta G naught divided by del T at constant pressure, or it may be written as T into del delta G naught divided by del T at constant pressure is equal to delta G naught minus delta H naught. From here we get d natural log of Kp divided by dt is equal to delta H naught divided by RT square. This equation is called Wentz-Hoff equation. In this equation, delta H naught represents the standard enthalpy change. However, it is found that the most of the cases delta H can be replaced by delta H. And the equation may be written as d natural log of Kp divided by dt is equal to del H divided by RT square. Integrated form of Wentz-Hoff equation. Equation 4 may be written as d natural log of Kp is equal to delta H naught divided by RT square dt. If the equilibrium constant changes from Kp1 to Kp2, when the temperature changes from T1 to T2, then the integration of equation 5 becomes the appropriate limit gives log Kp2 divided by Kp1 is equal to del H divided by 2.303 R into T2 minus T1 divided by T1 T2. Delta H in this equation is taken as the average value of the temperature range T1 to T2. Equation 7 can also be calculate the value of the equilibrium constant at any temperature provided value at some other temperature is known, as well as the value of delta H is known. Alternatively, if for a reaction the value of equilibrium constant at two different temperatures are known, the value of delta H for a reaction can be calculated. Wentz-Hoff equation in terms of Kc ratio Kp is related to Kc according to the equation Kp is equal to Kc RT power delta N, where delta N is the change of number of moles when the reactants change into product, taking logarithm to the both of the sides, differentiating this equation with respect to the temperature, but according to equation 3 also derived above. Combining equations we get delta d natural log of Kc divided by dt is equal to delta H naught minus delta n RT divided by RT square. Further, we know delta H is equal to delta U plus P delta V, or if the substances are taken in their standard states, we may write delta H naught is equal to delta U naught plus P delta and delta V, or delta H naught minus delta nRT is equal to delta U naught. Substituting this in equation, d ln Kc divided by dt is equal to delta U naught divided by RT square. where delta U naught is the change in the internal energy of the reaction when all the reactants and the products are taken in their standard states. Explanation of the effect of temperature on equilibrium as predicted by Le-Chatelier's principle. According to Van 't Hoff equation, from equation 3, del natural log of Kp divided by del P at constant pressure is equal to del H naught divided by RT square. If delta H naught is more than 0 endothermic reaction, then delta ln Kp by del T is positive and Kp increases with increase of temperature, but increase in the value of Kp implies that equilibrium shifts towards products. In other words, the endothermic reaction increases of temperature shifts the equilibrium towards products. If delta H naught is less than 0, that is the exothermic reaction, the value becomes negative. That is, Kp decreases with increase of temperature, which implies that equilibrium shifts towards reactants. These are exactly the same results as predicted by Le-Chatelier's principle. 4.16 Le-Chatelier's principle. The effect of concentration, temperature, and pressure on a system in equilibrium can be predicted with the help of a generalization first proposed by a French chemist, Le-Chatelier, in 1884. After the name, the generalization is known as Le-Chatelier's principle. It states as follows. If a system in equilibrium is subjected to a change of concentration, temperature, or pressure, the equilibrium shifts in a direction that tends to undo the effect of the change imposed. Let us now discuss the effect of the various factors one by one. First, effect of change of concentration. Consider a general reaction. A plus B is in equilibrium with C plus D. If to this reaction in equilibrium more of A and or B is added, then according to Le-Chatelier's principle, the effect will be to decrease the concentrations of A and B. This is possible only if of A and B reacts to form C and D, that is, the equilibrium shifts in the forward direction. Similarly, the effect of adding more of C and D to the reaction in the equilibrium will be shifted in the backward direction. The effect of change of concentration on the reaction in equilibrium can be very easily seen in the laboratory with the help of the following reaction. Fe3 positive plus SCN negative is in equilibrium with FeSCN2 positive. That is, if to the solution of a ferric salt, that is ferric nitrate, which is pale yellow, a solution of sulfocyanide salt, that is KSCN, is added, a reddish brown color is obtained due to the formation of ferric sulfocyanide complex ion. Now, if to this solution more of ferric salt solution of potassium sulfocyanide solution is added, the color of the solution becomes darker, showing the formation of more of FeSCN2 positive ions. Again, if the solution is small amount of the potassium sulfocyanide capable of giving FeSCN2 positive ion is added, the darkness of the solution decreases, showing that the equilibrium has shifted in the backward direction. Similarly, to study the effect of decrease in the concentration, a small amount of NaF may be added to the reaction mixture. It combines with the ferric ion as follows. Fe3 positive plus F negative is equal to FeF2 positive. Fe3 positive plus 2F negative is equal to FeF2 positive. Thus, the concentration of Fe3 positive ions decreases, the intensity of the color of the solution is found to decrease, indicating that the equilibrium shifts backward. The effect of the change of concentration can also be predicted by comparing the reaction quotient with the equilibrium constant. Let us consider the general reaction. A plus B is in equilibrium with C plus D. Kc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Suppose concentration of the reactant, concentration of A or concentration of B is increased, so that now we can write Qc in place of Kc. Qc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. As concentration of A and concentration of B has been increased, Qc will become less than Kc. In order that equilibrium is re-established, Qc will tend to increase till it becomes equal to Kc. This can happen only if concentration of A and B decreases and concentration of C and D increases. That is, equilibrium will shift in forward direction. Similarly, it can be seen that the effect of removal of product C and D shifts in the equilibrium in the forward direction. This has a great significance in the industrial processes, because if the product is recovered side by side, the equilibrium will shift in the forward direction to form more product. The removal of product is especially easy if it is gas. For example, first, in the manufacture of NH3 by Haber's process, NH3 gas is liquefied and hence removed side by side from the reaction mixture. Second, in the manufacture of the quicklime, by decomposition of CaCO3, the gaseous CO2, which is one of the products, is allowed to escape. Looking at equation 2, it may be noticed that continuous removal of the product keeps the value of QC less than Kc. As a result, the reaction continues to move in the forward direction. Thus, in general, if in a reaction in equilibrium, the concentration of any reactant is increased, the equilibrium shifts in the forward direction. On the other hand, if the concentration of any product is increased, the equilibrium shifts in the backward direction. The reverse happens if the concentrations are decreased. Second, effect of change of temperature. The change of temperature alters the state of equilibrium for only those reactions in which either heat is evolved or heat is absorbed. In fact, every such reaction is made up of two opposing reactions. If the forward reaction is exothermic, the backward reaction will be endothermic and vice versa. First, consider the exothermic reaction. N2 plus 3H2 is in equilibrium with 2NH3. Delta H is equal to minus 92.4 kJ. Or it may be written as N2 plus 3H2 is in equilibrium with 2NH3 plus 92.4 kJ. Obviously, the forward reaction is in exothermic, whereas the backward reaction is endothermic. Now, if the temperature is increased, that is, heat is supplied to the system, then according to Le Chatelier's principle, the equilibrium will shift to that side that absorbs heat, that is in the backward direction. Similarly, decrease in temperature will shift the equilibrium in the forward direction. Second, again consider the endothermic reaction. N2 plus O2 is in equilibrium with 2NO. Delta H is equal to plus 180.7 kJ. Or it may be written as N2 plus O2 plus 180.7 kJ is in equilibrium with 2NO. Obviously, here the forward reaction is in endothermic, whereas the backward reaction is exothermic. Arguing as before, the increase of temperature will favor the forward reaction while the decrease of temperature will favor the backward reaction. Thus, in general, exothermic reactions are favored by low temperature, whereas endothermic reactions are favored by high temperatures. Third, effect of pressure. This factor has a significant role to play only in case of gaseous reactions and those two which proceed with a change in number of moles. First, consider the dissociation of N2O4 into NO2. N2O4 is in equilibrium with 2NO2. Here the forward reaction occurs with increase in the number of moles, therefore the backward reaction must proceed with decrease in the number of moles. If now the pressure on the system is increased, the equilibrium will shift to the side in which the pressure decreases, that is to the side which is accompanied by decrease in the number of moles. Since backward reaction takes place with decrease in the number of moles, so an increase in the pressure will favor the combination of NO2 molecules to produce N2O4, that is suppress the dissociation of N2O4 into NO2. Conversely, if the pressure of the system is decreased, the equilibrium will shift in the forward direction, which is accompanied by increase in total number of moles. In other words, decrease in pressure favors the dissociation of N2O4 into NO2, that is increase in the dissociation of N2O4. Second, now consider another gaseous reaction involving formation of ammonia. N2 plus 3H2 is in equilibrium with 2NH3. In this equilibrium reaction, the forward reaction is accompanied by the decrease in total number of moles. If the presence of the system is increased, pressure of the system is increased, then according to Le Chatelier's principle, the equilibrium will shift in that direction in which a decrease in the total number of moles take place, that is in favor of formation of ammonia. Thus, higher the pressure, the greater would be the yield of ammonia. If on the other hand, the pressure of the system is decreased, the equilibrium will shift in that direction in which increase in the total number of moles occurs, that is in the backward direction. In other words, a decrease in pressure will favor the dissociation of NH3 into N2 and H2. Third, lastly, consider the following equilibrium reaction involving the formation of hydrogen iodide. H2 plus I2 is equal to 2Hi. This reaction takes place in either direction without change in the number of moles. So, according to Le Chatelier's principle, pressure will have no effect on the equilibrium. In general, low pressure favors those reactions which are accompanied by increase in the total number of moles, and high pressure favors those reactions in which take place with decrease in total number of moles. However, pressure has no effect on an equilibrium reaction which proceed with no change in the total number of moles. The effect of change of pressure can be predicted by comparing the reaction quotient with the equilibrium constant as done in the case of the study of effect of change of concentration. Let us consider the reaction N2 plus 3H2 is equal to NH3. Suppose the reaction mixture is enclosed in a cylinder fitted with a piston at constant temperature and a definite pressure. When equilibrium is attained for the equilibrium concentrations, we have Kc. Now suppose the reaction mixture is compressed to half the volume. The pressure is doubled. The molar concentration of each of the reactants and products will be doubled, so that now the reaction quotient is Qc, that is 1 by 4 of Kc. Thus Qc is less than Kc. The re-establish of the equilibrium Qc will increase till it becomes equal to Kc. This can happen only if NH3 increases and concentration of N2 plus H2 decreases. That is, equilibrium will shift in the forward direction. It is important to mention here that in the study of effect of pressure on reactions involving heterogeneous equilibrium, the solids and liquid reactants of products are not taken into consideration, as the effect of pressure on them is negligible. For example, for the reaction 2C plus O2 is in equilibrium with 2CO. QC CO, concentration of CO divided by O2 is equal to QP is equal to PCO plus PO2. Thank you.